Thank you. Is it okay now? Okay, good. Sorry. Thank you for telling me. Shut the door. Okay. So, computing moments. Right, so this is what we saw last time. So let O be some operator, CD tensor K, right? And we saw that this is like the brief version. Then the moment operator, let's just write it as M sub K, right? O, which recall was defined as expectation or unitary is taken from the Haar measure, K copies of the unitary dagger. Silent. Do not disturb. Okay. So this would give you sum over pi sk c pi, the operator, and the permutation. Right. So this is what we proved last time, that one can express any moment operator acting on O in terms of permutation operators, right? And so there were a few small remarks about this that the paper mentioned. So let's look at them. Okay. So the first thing the paper mentions is that so one can explicitly compute C pi over. Actually, the theorem also said this relation, right? So it said that C pi can be, okay, let me write it down. It said that one can obtain C pi, like there was this relation that we had derived. So we said that trace V dagger d sigma O is the same as sum over pi sk C pi O trace V dagger d sigma Vd pi. Right, or you can write it as Vd sigma inverse pi. That's probably better. Right. So this was the statement we had last time. So now what the story is that, so one can actually write this more explicitly as follows. So it's not saying anything really very deep. It's just saying that you can invert a matrix. So, but it's good to know the words. Trace V dagger sigma acting on O. Okay. Yeah, so this is like V dagger D sigma, whatever, doesn't matter. And this object is called the, okay, so this is the pseudo inverse of G, where G is defined as, so G pi sigma is defined as trace V dagger, so it's just that matrix we had, pi inverse sigma. Because that's not surprising. What is good to keep in mind is that this object G dagger is also termed the Weingarten. Okay, yeah, maybe I should just write it. Okay, so the second point is that one can write G dagger pi sigma. One can define this to be what's called the Weingarten so this is the Weingarten coefficient somehow. And this is nice because this in turn can be written as written in terms of the characters of the symmetric group. Characters of the symmetric group. Okay. But we'll not go into the details. I also don't know the details. But this is good to know that that the pseudo inverse that we're trying to compute is like a known quantity. So once you know the permutation itself, there are like some fixed functions, in particular characters of the symmetric group, using which you can actually compute this explicitly, and that in turn allows you to compute these coefficients C pi, which allows you to write any the moment of any operator in terms of permutations and the coefficients. Okay, so that's the story. And G itself is called the Gram matrix. Yeah, so let me write this. Okay, so the Gram matrix G itself has a simple expression. In terms of cycles. In terms of the cyclic structure of the group. Okay, so what that means is that G pi sigma, which is the trace of, just from the definition, right? So pi inverse sigma is basically d to the number of cycles of pi inverse sigma. Okay. So that's kind of an interesting statement. So you know that all okay. Are you still reading? I don't know where you are. Are you with me? Do you need a minute? You with me? Okay. So here the what is being said is that this matrix G, which is essentially this one, right? So this we define to be G in terms of pi and sigma being the coefficients, right? And what we're saying is that this, when you take the trace of this object, if you take trace of this matrix, this permutation, this is nothing but d raised to the number of cycles in the permutation. So we know that every permutation is just a bunch of cycles, right? So this is the case, and why is that? So this is basically because it follows from the following observation. So Pd pi. So if you write the trace, this is nothing but I1 to ik, which with each index going from 1 to d. So you have I1 pi inverse 1 all the way to ik, and then I pi inverse k. Okay, and then you have to draw some diagrams to convince yourself. Okay, so for example, if you have, suppose you have identity, okay, and let's imagine you take the element to itself, right? That's what's happening. So these are the different systems. You're taking all the elements to itself. So here, when we write these down, right? So you will have elements like 0, 0, 0. So you permute them, they'll stay 0, 0, 0. Okay, then you'll have like 0, 0, 1. You'll permute it, it'll stay 0, 0, 1, and so on. So regardless of what element you take, you would have all contributions coming from them. So each one of them is going to give you a d. This is going to give you a d, this is going to give you a d, and so on. Okay, so you get d to the however many cycles you have here. If you had something else, like suppose you had a cycle like that, right? And say this was a self thing. Okay, suppose this was your permutation. Then when you do the loop, right? So you'll have to start with 0, 0. 0, 0 will be okay, because 0, 0 will always be okay. Nothing is changing. All elements are the same. But if you have 0, 1, right? Oh, sorry, 0, 0, 0, for example. These two are these ones. Okay, you're following what I'm doing, right? With the dots and the. So each of these I'm thinking of as a qubit or a qdit, whatever, and then I'm looking at the state of the qubits. Okay, and these are just permutations across the qubits. So if 0, 0 will obviously get mapped to 0, 0, the last one doesn't change. So this is actually true even if you put like a b here. So it's true for all b, right? This will be 1 in general. But if you have a 0, 1, forget the last one, okay? And then the permutation will flip it, right? It will make it 1, 0, b. So this will give you a 0, okay? So in order to get a 1, you actually have to have these elements be the same, okay? So then the whole thing will basically contribute whatever the dimension d is, and this one will contribute d. So it will be d to the number of cycles. Okay, that's just the intuition. You can work out the details. Okay. because the other ones are going to cancel out. So these have to be exactly the same. Otherwise, in the permutation, one of the terms would be different and they'll get cancelled. Okay, so this is the part about the cycles. Okay, so and that's the proof sketch. So let me not spend too much time. Okay, now proposition 11 says the following. Okay, maybe one thing I should mention is that the main statement that I wanted to prove was, so this is the goal, okay, this is why we are doing all of this, because in Andrea's lecture we had this statement that expectation of u, like the Haar measure, over the Haar measure, u tensor k, phi tensor k acting on u tensor k. This object is the same as permutation dk. We haven't defined this yet, but this is the the symmetric permutation projection on the symmetric subspace. Okay, divided by a trace of this same thing. Okay, so this is really what we are trying to prove at the end of it. So all of this machinery that I'm telling you about is in service of being able to prove this in the end. Okay, and the problem is I have not been able to read the proof. I was like just started reading this. It's like one more page, but there's a bunch of background. So hopefully we'll be able to cover the background, and I can tell you the final proof next time. Okay, so proposition 11 says the following. So suppose you have a permutation from the permutation group. Okay, then the permutation matrices corresponding to this permutation, PD pi. This is the proposition I left you with last time. They're linearly independent if k is at most t, but linearly dependent if k is greater than t. Okay, so that's the statement we're now going to prove. So let's start. Okay, so we're going to look at the case where k is at most t. So we're going to look at this, the linearly independent case. Okay, and the proof is kind of cute. So suppose, I have to learn how to write while showing the board. Okay, so you have these permutations, right? Suppose they are linearly dependent. Okay, we want to prove that they are independent, but suppose for contradiction that they are dependent. So basically we assume.
I missed the previous class. So PD pi is like d-dimensional unitary representation of pi.
Yeah. So it's just this object. So I1 to ID, and then where was the pi inverse? I think it was here. Sorry, I messed up. Okay, so pi inverse 1, pi inverse d. Not d, k. So depending on how many elements you have.
No, I index will go to d, but pi is minus k.
Wait, what am I messing up? Pi is no. Each of these i's goes from 1 to d, so it's fine. But it's on k, right? Yeah, there are k elements. It's fine. Yeah. Okay, and then this is I1 to Ik. Sorry, I got confused. Because that's the definition of the permutation. You're just taking these elements and then moving them around. There are k systems, right? So each system.
Right? Huh? There is sum over what?
Oh, this is just sum over i's. So I1 to Ik, each one of them is d. Right. So that's the recoil. It's just permuting the objects, nothing very deep happening here. Okay. So whichever state you're in, you just move that element to whichever new location. That's it. And you're doing it for whichever state they're in.
This is CD tensor k.
CD tensor k, yes. Exactly. Okay, so we have k is copies of k many d-dimensional systems. Okay. Yeah, if something's unclear, ask. Okay, this is good. Okay, so the permutations. So these are the permutations that are indeed linearly independent. So we're making that assumption. So what that means is that there would exist alpha pi in complex numbers, such that for all pi in Sk, it holds that alpha pi Vd pi is 0, sum over pi Sk. I don't know why I've written for all pi. Okay, this is just that it's a complex number for all pi, sorry.
There will be such that alpha pi equal to 0.
Yeah?
You are saying linearly.
Yeah, that
right?
they're dependent. Yeah. So there's 0.
Yeah, so this means sum of the alpha pi is non-zero.
Yeah. So what we'll show is we'll show that all alpha pi turn out to be 0 if this has to be true. Okay. Otherwise, of course. Okay. So that's the statement. So yeah, not all 0. Not all 0. It's slightly sloppy. Sorry, but you get the idea. Okay. Right. Okay. So how do we see this? So we're going to do the following. So we'll choose k distinct elements I1 to ik, okay, each one of them taking values 1 to d, okay, and note that we can, because we assume that k is at most d, right? So I have d many options and I have to only make k choices, so I can choose them to be distinct. Okay, and so we note that sum over pi in Sk alpha pi Vd pi acting on I1 to ik, okay, this would be equal to pi Sk alpha pi acting on I pi inverse 1 I pi inverse k. So was there a question or? Okay, sorry. Okay, so this is fine. We just applied the permutation, so that's not a big deal. Okay, so the second note is that what we'll do is we'll multiply on the left. So left multiply by the following. So sigma inverse 1 to sigma inverse k. Okay. To get alpha sigma is 0. Okay, so why is that? So let's check why this is going to happen. So let's just do the multiplication. So this is the ket, right? We're going to act it on pi inverse 1 to I pi inverse k.
So pi equal to sigma will contribute to get alpha.
Okay, so this will be 0 exactly. So this will be 0 if sigma is not equal to pi, right? Because at least one element is different, so the inner product would vanish. And this is going to be 1 if sigma equals pi, right? But this equation, sorry, where was it? Yeah, so by assumption the whole thing has to be 0, right? So basically singling out alpha sigma, and we are concluding that alpha sigma is 0, and this we can do for all sigma. Right, so that means that for all alpha this is going to, like for each alpha we can show that it's going to be 0. So the only way this thing is 0 is if all alphas are 0, so they're linearly so they're not linearly dependent, so there's no combination that would give you 0. Okay, so that's the argument. Okay, so let's quickly read this. So conclusion, this is true. So for for all sigma. This works for all sigma. Right. Okay, so the conclusion is that VD pi are linearly independent if k is at most t. Okay, so now let's look at the case where k is strictly greater than d. Okay, so this one's actually more interesting. This one was relatively expected. The other one's a bit more interesting. Yeah, let me actually remove this part. It's fine. Okay. Okay, so yeah, let me write it properly. So case k greater than d. So in this case, what we're going to do is we will look at the following. So we consider A defined as follows. So you take SGN of pi VD pi. Okay. And so basically we're showing that this linear combination of permutations with coefficients given by the sign of pi will actually be 0. So we'll show that it's linearly dependent. Okay, and probably you can already see this, but so strategy is show A is 0. Okay, so yeah. So consider action of A on I1 to Ik. Okay. So we'll note that there exists L not equal to M, okay, where L and M are going to be, which system we are choosing. So there are k many systems. So we are looking at two distinct systems. So what we're saying is that there exist two distinct systems such that they are encoding the same state. Okay, and this is basically just because k is strictly greater than d. Okay, so it has to repeat, right? You only had d many options, and you have to have k many systems. So some of them have to have the same state, right? So this is fine. And okay, so now the strategy is, so we use anti-symmetrization. Right, because like intuitively we already know if there are repeating elements and you're taking an anti-symmetrized sum by fermions and stuff, we know that it will disappear. But we can do it more formally, so we can check. So note that I1 to Ik is going to be A VD. So tau Lm is just it's permuting, so it swaps systems L and M, right? And looks bad. Okay, so I1 to Ik is the same as if you apply this permutation. Nothing changes, right? Because they have the exact same state from the assumption. Okay, and what that means for us is that we can expand the definition of A. So if you expand the definition of A, Sk, you'll get sine of pi Vd pi Vd tau Lm I1 to Ik. Right, so I've done nothing, I've just written down the definition of the linear combination, and this one can combine as Vd pi tau Lm, right, which is why we were defining all of these things with inverses, so the composition is straight, which I didn't realize earlier, but that's why we're doing it. Otherwise you would flip the composition, which is not as nice. Okay, so we have that, and
That was the region of inverse.
yeah. I mean, that's my understanding. Like if I were to do, yeah. Like if I had to set the convention, I think it's convenient to have this and write inverses just in the definition itself. Okay, so we have this, And now what we can do is we can write the sum. So we can absorb, because the sum is running over pi, I can replace the summation variable pi with pi gamma inverse, or sorry, pi tau inverse. So that would give me sine of pi tau inverse. So I'll not write lm, okay? So this is implicit now. So tau is tau lm. It's just notation. Okay, so sum over pi in sk, sine of pi tau inverse, v d pi, I1 to ik. Okay, and this is going to be the same as the sine of tau inverse, sum over sine of pi, vd, the permutation corresponding to pi, acting on I1 to ik, sum over pi. And now this object is the same as a of I1 to ik. And we get a minus sign because yeah, so you're doing, yeah, exactly. So an odd cycle, the inverse of an odd cycle is also odd, so the sign is going to be minus 1. Okay, because the identity is an even cycle, so odd times odd has to be even. So. Okay, so you get a minus sign, and okay, so and then basically this means that I1 to ik is 0. Okay, and then this you can do for, regardless of which I1 to ik you choose, there has to exist such an LNM. So you can argue for every computational based element that A is going to act as and give you 0. Okay.
But if they repeat it 2 times, then
no, but the argument is still true, right? Because I'm just applying this for whichever one system.
yeah, but if there are 2 flips, then you will have
Yeah. No, it's still true that if I do one flip, I will get.
or you will not flip the other.
Yeah, I will not. All I have to show is that there exist at least 2 elements which are the same, and swapping those will not change anything.
Yeah, it's insensitive whether others are same or not.
Yeah. Yeah. Okay. Good. Very nice. So that sort of finishes the proof of this proposition. Now there are some baby things, so let's do them. So it's useful. It's going to be useful to define something very basic. So we'll define identity and swap, or rather flip. Oh yeah, let's just call it flip on 2 systems, or basically when k equals 2. So here's the definition. So identity is of course no surprise. So identity is defined as psi tensor psi will give you psi tensor psi. Oh, maybe I should write phi actually. Right. So this is for all phi psi in CD tensor. Oh, it's just CD actually. Okay. So for all phi and psi, identity is this, not a surprise. And then the swap operator is defined as psi tensor phi, gives you phi tensor psi. Okay, so nothing very surprising. What is kind of cute is, well, okay, I know, maybe there's one quick note. So identity, of course, we know we can write like this, right? So you have sum over ij in D, and you just do ij, right? So that's not a surprise. The F operator would be what in this notation? Exactly. So it's ijj, right? Okay. So that's kind of nice. And as an immediate consequence of that, let me ask you the following. So this is called the swap trick, apparently useful later. So trace solve A tensor B with the flip operator acting on it. What do you think it would be in terms of trace on a single system?
They know.
Huh?
They know.
Oh, they already know? Okay.
Shreyas will tell.
Huh?
Oh, Shreyas is that here.
Okay.
Shreyas ID.
Right. Exactly. So this is, it's sort of cute. Basically, you just use the definition, right? So you're using the fact that ij A tensor B, ji is basically I A j j b I, and that sort of gives you the thing. Okay. It's not very deep. Okay, good. So that part is good. Okay, so the story is just that these are useful. That's what the text is saying. That's fine. And the second point is we now look at a corollary. Corollary of theorem 10. So theorem 10 was, remember, the superposition thing, right? That you can write the moment operator as a sum of permutations of. So what we're going to do is we're going to look at the two-dimensional case and the one-dimensional case. So this is what I think Uttam was saying when I first wrote down the statement, the general statement that you can write any moment operator in terms of a sum of a linear combination of permutations. So the first thing he said is that when k equals 1, it should be that it's proportional to identity, and I couldn't see it right away. And I think Shreyas had pointed out the answer, which was that if you have only one system, the only permutation you have is identity, right? In terms of swapping. So that's exactly this statement, that if you have only one copy and you have U O U dagger and expectation, so this will be trace of the operator divided by D times identity on that system, right? And I just gave you the proof, but the second one is a little bit, this requires just a little bit of calculation, so let's do it. It's very, all of these things are elementary, but I think it's good to do them once. Okay, so given this, so now if you have two copies, if you have two systems, then it holds that U acting on mu H, U tensor 2, O U tensor 2 dagger is going to be the following. So you'll have the first component, which is written as C identity, and then the second component is C flip, right? Because if you have two systems, the only thing you can do is identity and swap them, right? There's nothing else you can do. So it has to be a combination of these factors, and these factors, we'll write down what they are, okay, in just a moment. So you can explicitly, actually, maybe I should compute them, because that's the whole point of the theorem, that you actually can find them. So this is trace O minus D inverse trace FO, D square minus 1, and this object is trace FO minus D inverse trace O, D square minus 1, right? Okay, so we're done with the proposition. We can use the rest of the board. You know, while you're erasing, you realize that the board is not exactly flat, like there's a little bump. Yeah, like you can feel there's a joint here somewhere. Anyway, it would be very cool if they had the sliding boards. Those are very useful. Okay, so now, so let's do the proof. So for the first one, recall theorem 10, right, which says that you can write expectation U O U dagger. Like this thing has to be in the span of permutations on S1, right? And this is like basically just the identity, so that immediately gives you the result. You take trace and then you take trace, right? Right, so trace of identity gives you D, and so that's why you get that. So this part is fine. Second part is we're going to proceed essentially in the same way. So proceed similarly. And like I said, S2 has identity and F, right? So what that means is that when you take the expectation, right, so we just get this object identity plus CF F, right? And now we want to solve this, and how you solve it is also, any guesses? Because obviously we'll take the trace on both sides, so that will give us one set of things. What else can we do? We can multiply with something, right? And the only other reasonable object we have left is F. So if you multiply with F and take trace, you'll get the second equation, right? Because they swap. Okay, so this is the strategy. So strategy. So first you take trace.
In terms of Weingarten coefficients, right?
Yeah, those are, so we didn't cover the details on how you expand the Weingarten, because those apparently you can write in terms of the character of the matrix and so on. Probably those things are related, but the review doesn't go in more detail, and I certainly don't know the details myself, but something to study later, yeah. Okay, so you multiply with F and trace both sides, right? So when you do this, you're going to see the following. So you'll get trace O is going to be identity D square plus CFT, right? So why is the trace of F D? That's where we use this fact, right? So you just take identities and so you'll get D. Okay, and then trace of FO, right, is going to give you what? It's going to give you C identity O D plus CF D square, right? Because they just get flipped. Okay, and now it's a system of linear equations which you can solve directly. Okay, and when you solve it, you'll get that. Alrighty, so we're done with the first set.
So you proved this is time result.
Wait, what?
Like the integrals are with span of permutation.
That we did last time. Yeah. Did we do it last time? Wait, let me recall. I don't think we did the permutation one. That is sure while duality, and I'm going to do a special case of it a little bit later. The proof is actually, I think, much more involved. The notes did not cover this. Yeah, we're just using the theorem and deriving a corollary.
Once you know this permutation result, then it's simpler.
Yeah, for sure. So actually, we will prove the permutation result for until 2 copies. So we'll show that it's actually.
Weingarten also you can compute for 5-6 copies. After that, it's.
I see. Yeah. So we have. Okay, good. Yeah, I have a feeling I might run out of material today. Let's see. We're going quite fast. Very good, very good. Yeah, I wish I could complete that last little theorem. That would have been very nice. Okay, so now we're going to do exactly what Uttam Bhai was asking. So we now prove the special case of sure while duality, which was the permutation statement. But for like a special case, let's prove a special case. So the special case being k equals 1 and k equals 2. so we show that the commutant, I guess it was called D of K, is going to be in the span of EB pi in SK. Okay, and here we already showed that this M, this was the like this thing is in the commutant of the unitary groups. Right, this expectation we already showed using the properties of the Haar measure. Okay, so that's why we could apply the duality. Okay, so example 14 says the following. Says that the commutant UD for k equals 1 is span of identity. Okay, and the commutant for UD k equals 2 is span of identity and F. So this is identity on one system, this is identity on two systems. It's just a slightly different notation. Okay, so let's start with the proof. Okay, so let's start. So consider an element A inside commutant UD k equals 1. Okay.
Really good to define commutant. So UD is group here, right?
Yeah, yeah. So commutant was we already defined it, but no. It's good. We can recall the definition. Yeah, exactly. The only difference is that you have to do tensor k. That's it.
Yeah, no, right.
Oh, but you already know the. Okay, good. Oh, you were saying because for other people I didn't define it. Yeah, we did it in the last lecture. Yeah. Okay, so now you guys remember, right? We did it, right? Yeah, okay. Like I'm not hallucinating. Okay. Okay, so in the canonical basis, right, one can write the following. So A is sum over ij in D, aij, ij. Right. So far I've done nothing. I've just written the matrix elements, and then what one can do is one can write the diagonal term separately. So 1 to D. So aii, ii, plus sum over I not equal to j, aij, ij. Okay, so I just removed the diagonal element. Haven't done anything very deep. Okay, and then I have the note that uk. Oh shoot, sorry, I messed this up. Okay, so u dagger equals a, right, for all u, right? This is simply because of the definition of the commutant, because it's in the commutant of, right? This is fine. And then we consider u sub k, which is defined as follows. So u sub k does the following. So whenever I is not equal to k, it does nothing, and whenever it sees a k, it adds a phase, -1. Okay, so that is maps k to -k. Okay, everything else is the same. Right, and now we look at uk dagger, as you may have guessed. Okay, so we'll use this fact. So what that would imply is that alk kl has to be the same as minus akl kl for all k not equal to right? Because when you have k on both sides, the sign won't contribute, right? It's minus 1 squared. So if you have k on one of the indices, you will pick up a phase, right? And so that basically tells you that you cannot have off diagonal elements, right? And you can repeat the argument for all k.
Also LK, right?
What?
Right hand side minus a LK, not k.
Yeah. Sorry. I got excited.
That's correct.
No. I think I was thinking of something else when I wrote it. Okay. Yeah. Okay, and this holds for arbitrary k. This holds for arbitrary k. Okay, and so this basically means that. So we managed to simplify the form away, right? So now we know that A has to be of this form. We still haven't proved that it's proportional to identity, but at least we know that it's diagonal. So we have this. Okay. Now,
Nice.
yeah, these are very cute calculations once you know them. Okay, and basically the whole idea we're using is that you have access to these permutations and it's supposed to stay invariant under these permutations, right? Because it's invariant under all u's, so you can choose specific u's and derive properties that the coefficients have to satisfy. So in this case we looked at, if I add a phase, what is the consequence? Now we'll apply some other unitary and see what is the consequence. In particular, I think we'll permute the matrices, the elements, and then we'll see what happens. Okay, so we look at, so UKL is defined as follows. So whenever I is not one of these, okay, so it's neither K nor L, you do identity, okay, and when it's L you make it K, and when it's K you make it L. Okay, so you're just swapping them. Okay, so UKL sends K to L and L to K. Okay. So now note that if you apply UKL on A U dagger UKL, you're going to get A, right, just by the same argument. And what that means is that AKK must be the same as ALL, right? By exactly arguing like we did here. So you can look at specific entries. Okay, and so what does that mean? That means that not only is it diagonal, but all diagonal elements are the same, right? Because K and L were arbitrary. So you can run the argument for all of them. So conclusion, that A is going to have this form. 1 to D, I, and C you can choose to be whichever one you want, right? Which is exactly what we asserted, that is basically C times identity. Because it's a one-dimensional. Okay, so that proves the first part. So now you can sort of start seeing how the second part would happen, right? So far we did not have any, we were applying unitaries, but on a single system, right? There was no cross-system unitaries that had to be applied. But later we'll also start applying cross-system unitaries and see what constraints they impose. Okay, so let's do it. So consider, so suppose Q is now some object or some matrix in the commutant, K equals 2. Okay. So we first note that Q can be decomposed as follows, right? So we have IJ KL, okay, going from 1 to D, Q IJ KL, IJ KL, right? Just writing a general matrix. Now, the second note says that U tensor 2 acting on A, U tensor 2 is going to give you A, right? For exactly the same reason, right? As before, because it's in the commutant. So this is true. Okay. Yeah, I don't want to remove the theorem statement. So yeah, let's just use these two parts of the board.
While you will find different views and try to
Yeah, it's the same idea. Exactly. The only cleverness is in like which use you choose and whether you can get a clean form.
at the end must get some diagonal which are equal and then some swap.
Exactly, because we know what the answer is. so it's true that this is what we want. Okay, so let's see how we get that. So the unitary that they consider here is again similar. They add a phase. So UK prime is defined as, I'm writing K prime because now we're already using K as an index. So it's a slightly clunky notation, but okay. So whenever I is not equal to K prime, you do the same thing. Otherwise, you send K prime to minus K prime, right? So you add the same phase. Okay. So let's see what that means here. Oh shoot, did I mess up? Sorry, I missed. Sorry, I missed.
Oh no, okay.
Yeah, I think.
No, you will take tensor to.
Yeah. So I think it's applying on only one system. I guess you're taking identity. Okay.
You will have UK prime tensor to that you will apply.
Right. So UJKL. Yeah, exactly. Because you're applying the same unitary on all the systems. Sorry, you're right. You're not supposed to have a global unitary. Yeah. Damn it. Thank you. Okay. So IJKL are such that IJ is not the same as KL. Okay. So you take sum over all four indices such that the first two indices are not the same as the second two indices, unordered. Okay. So none of the elements actually match. Then it holds that.
You said this is not ordered.
Yeah, these are sets. So I'm saying the sets are distinct. So it's unordered. Yeah. Okay, so it holds that IJKL is going to be minus QIJKL IJKL. Okay, and this basically is implied by the fact that this is going to be true, and for some K prime.
Tensor to.
Huh? Yeah, exactly. Sorry. Right. So basically, we wanted to make sure. What are we trying to do? We're trying to make sure that only one phase is picked up, right? So we're saying suppose all the indices are distinct, right? Then there has to be at least one K prime which would give you that sign, right? But because you can apply the unitary and then run the argument we ran before. Okay. So what does that give us in terms of the form of the construction? Thus, Q has the following form. Wait, I only have half an hour more? Oh, okay, so then we're going a bit slow, shoot. Okay, so then Q has the following form. QII II. So this is the diagonal part, right? Then you have I not equal to j, Qij, ij. Okay, this is also the diagonal part because the indices are the same, right? Okay. Then you have another I not equal to j, ji, ij, ji. So this is an off diagonal term, right? Okay. and that's it. And the reason is that, so we had ij is equal to kl, right? Because when they're not equal, we already argued that those terms will not exist. So what are the ways they can be equal, right? So at least one of them has to hold. Okay, so you will either have that I is k, j is l, right? So I is k, j is l, or the other way, or you'll have I is l, j is k, right? Or the last one where all of them are the same, right? Right, there's no other possibility. So those are the terms that we have. Okay. Okay. And this does look like a swap, right? A little bit. So. Yeah, but I guess that would be like a similar argument to what we did last time, right? So.
Again, it's the same unitary you are applying twice, and you don't
Right.
have much options.
Right. It's true. Yeah. I guess if you do enough of these cases, then maybe you'll see the general argument in true while duality. I don't know. I've never.
That is actually true.
Yeah. Yeah, it's a very nice tutorial. It's written like for babies, so it's very good. Okay, good. Now, so where were we? So we have this form, okay, and then now consider. So you have uij going to kl. No, actually, I think I misspoke when you were saying this, because no, it's fine, sorry. Okay, let's see. So now what's happening is ij are going to be sent to kl. Okay, so I prime j prime not equal to ij kl. So you sum over all indices such that none of these match. So I prime j prime, I prime j prime. Okay, so you have identity on when the indices don't match, and you have ij kl, and when they do match, you're going to do the following. Okay, so you're sending kl to ij and ij to kl. Okay, and all others are identity.
Yeah, this seems not.
Huh?
This is bipartite unitary now.
No.
Yeah.
I mean, in the sense that, wait, what am I doing wrong? But are we allowed to apply these unitaries? Because it's still applying U tensor.
Yeah, that is.
Yeah, okay, let's see. Actually, I think I kind of messed up. Maybe I have a feeling they're applying. Okay, let's see. U tensor 2. Maybe I actually wrote it wrong. It's possible. Wait. Let me double check. Okay, maybe I wrote the unitary wrong. Give me a second. Yeah, so here they're just saying that you write a unitary that exchanges ij with kl.
Yeah, so you had 4 terms probably instead of bipartite.
Yeah, so maybe that's why they didn't explicitly write it, because you needed to be. No, but even then it's acting on 2 qubits, right? So it's a little bit strange.
If they write get, then that is odd again. If they just say indices, then they probably mean individually, that I goes to k and then k goes to I, then j goes to l and l goes to j. based on the previous case, you had IJJI. Now I probably will have 4 terms.
Right.
But whenever I think I get intuition, it's wrong.
Right. Yeah. So let's build the correct unitary. Let's see what happens. Okay, I think I wrote this wrong. Sorry about this. So let's do the following. So we send I. Let's do what Uttambai is saying. So let's send I to J and K to L. Okay. So then you would have identity. This part would probably be the same. That you sum over. Let's say I prime J prime. Not in ij kl. So this part is I prime j prime. Actually, I can just keep it to be identity. I don't need the other one, so it's fine. I prime, and then plus the other term would be that you send I to j plus the Hermitian conjugate, I guess, and then plus k to l plus the Hermitian conjugate. Yeah, this is wrong. Sorry. Okay, so this is a unitary that does the exchange. They didn't explicitly write the unitary. I was trying to be explicit and I messed up. Thank you for pointing it out. Okay, good. So if you have such a unitary, okay, then it follows that if you use the same argument, U2 tensor Q U2 is the same as Q for this unitary. You have Q would become I equals 1 to D. So you can basically argue that the coefficients have to be the same. Sorry, say it again.
Those second and third summations.
Oh yeah, there are no summations. You're right.
But that is still exercise.
Huh? Why? This part? Oh, there's note. The note or this, the unitary. That's just the definition, so there's no exercise.
Yeah, because the unitary you did not double check, right?
Why? Whether or not it's a unitary, you mean?
No, it's unitary, but whether it will give you this result.
Yeah. So the note, this part is probably, we will not try to, we will probably do it as an assignment or something because, but the idea is roughly the same, right? Because when you apply the unitary, depending on which I and k you're targeting, you'll be able to flip them. And because I can send the II coefficient to whatever other, k, whatever, what is that? So KL, right? So I can send II to KK. So every time I do this, the coefficients correspondingly have to match, right? And then similarly for IJ, I can send it to whatever KL. So then the IJth coefficient have to match the KLth coefficient. So it's not really that much of an exercise, but okay, you can do it. Good. Hermitian conjugate. It's just so that it's a unitary, right? Because you have to act on all. Yeah, all good. Okay, very well. So we have this, and the second note is that so Q can also be written as, you can just use the definition of the identity and the phase flip, the swap operator, or which they're calling flip, to write it as follows. So B times identity plus C times F, right? Because each one of them will have the diagonal and off diagonal components. You can pull all the you can adjust all the diagonal components by changing the amplitude away, right? So you'll get this. So now we are very close, right? We're in good shape, right? Because we wanted to show that it's in the span of this. We just have this one extra object, and now they're going to argue that this will also vanish. So how they will show it is as follows. Okay, so let me actually do it step by step, as they've said. So now, because identity and F are already in the commutant, okay, Q is also going to be in the commutant, if and only if this term is in the commutant. Right, because everything else already commutes with all the unitaries. So the only thing that could cause an issue is this term. Okay, and the claim is that, as you can probably guess, that term is not in the commutant. So which means that this coefficient has to be 0 if Q has to be in the commutant, which is the assumption. Okay, so the claim is that sum I 1 to d I is not in the commutant. Okay, so let's do this.
So you will find a unitary that will change it.
Yes. So we'll show that. How did I prove it? I actually don't remember. Let's just do the proof. Let's see how it goes. So proof of claim or of the claim. So suppose for contradiction that this object is actually in the commutant. Is in the commutant. Okay. And now what we're going to do is we're going to consider the discrete Fourier transform. So U DFT. It's a bit of a heavy tool to use, but okay. Okay. Sum over JK omega J minus 1 K minus 1 JK. I guess this is slightly, they have a minus 1 because I think normally we sum from 0 to the thing and now we're summing from 1 to d, so I think they're just adding a minus 1 by hand to match the convention. And omega is defined to be e to the I 2 pi by d. Okay. So we consider this, then U DFT twice on II U DFT dagger has to be the same as the initial operator, right? So that's just by this assumption, and that should give us some contradiction, and the contradiction that we get is the following. So so this implies that if you compute 1 1 tensor 2 U tensor 2 1 1. Okay, so you take inner product with 1 1. The right hand side will be what? Right. And it turns out that this part is going to be is sort of an easy calculation to check. This would give you 1 by d. Okay, because so you have 1 by d. You just put the definition kk prime. So you're putting it on both. So I'm just pulling out the normalization for U tensor because we are applying it twice, so there's root d, so I'm putting a 1 by d directly here, and then omega to the 0 kk prime sum over I sum over k double prime k triple prime omega 0 k double prime k triple prime, right? Because I just applied a 1 1 and 1 1 would give you yeah, so say one of these terms is 0, right? Then it will be omega to the 0 already, and you're inner producting with 1 on one side, so you'll always get, so the phase won't really matter, you'll get a constant phase. And then the remaining part is so you'll have 1 by d square, right, from, oh sorry, there's a 1 by d here as well, right, because you're applying this twice, so there's 1 by d from here, 1 by d from here, so you get 1 by d square, and then this part in between is just identity, but like with on d dimension essentially, right? So you're going to get 1 by d square, and then sum over I, which would be 1 by d, right? Because I is running from 1 to d. So that's a contradiction, because on the one hand you're getting 1 by d, and on the other it should be 1. So there's no way that this object lies in the commutant. And that was the last step, right? Because so if this cannot lie in the commutant, it must be that a minus b minus c is 0, and then we have the form that we asserted. So that completes the proof. Alrighty, very nice. So
One outer product is not in the component. Just to show 1, 1, 1, 1 is not in the component is enough.
no, right? Because it's a superposition. It could be that.
Okay, other.
It could be that some superposition is in the commutant. I don't know actually, but we want to make sure that this entire sum is not in the commutant. So if you just argue that one term is not in the commutant, if you do it, yeah, the sum might still be in the commutant, right? Like you might pick up some, you know, it's not obvious to me maybe.
Because these unitaries can give phases, so things might get cancelled out if you so for one.
Right, yeah. For example, if you have, sure, that's true. That's true. Yeah, thank you for clarifying that. I hadn't thought of that. Okay, good. So now let's move on to the next thing. Yeah, I think we are doing well.
But what was the question? I didn't get the question.
I think he was trying to prove that, if I'm not mistaken, that individually the terms are not 0, and he was trying to argue that that's enough to prove the whole thing, which I wasn't sure it is. And then you explained why that is not enough without knowing what he said, which is surprising. Okay. So let's move on to the next topic. Yeah, we're doing good time actually. We might be able to make. Okay, so section 4 is symmetric subspaces. Right, because remember I erased the goal. The goal was that we wanted to show that the symmetric subspaces can be written as a sum of the projectors, right? So the coefficients are basically all the same. Because we already know from Schur-Weil duality that it will be in the span, but showing that the coefficients would be same is the non-trivial part. Okay, so what's the story here? So we're going to introduce, we'll introduce the symmetric subspace, and we know it plays a crucial role in Haar random states and so on.
So without integration, you got I and F both, but with integration, the F both will go there. With F is also symmetric. So this swap is.
We'll probably show B and C are the coefficients are the same. We'll not show that. Oh, you're saying if it's a symmetric subspace, then yeah, even in the symmetric subspace, I think it should be like the coefficients are the same.
I'm asking previous. So F lies in the symmetric subspace, or?
So I think the sum of identity and F would be a projector onto the symmetric subspace. That's the statement. By itself, of course, it's like a projector being in a subspace is slightly misleading. Yeah. So the projection identity plus F would project onto the symmetric subspace. Yes. So we'll prove these things as well. Okay, and then the symmetric subspace can be defined. So these are these are states that are invariant under permutations. Variant under permutations of the subsystems, right? Constituent subsystems. So that's the definition. Formally is also very simple. So formally we say that we define this space as the set of states psi in CD tensor K. So we have K copies of the system, right, such that VD pi acting on psi gives you psi for all permutations pi in SK, right. So this is fairly expected. Now we are going to define so it would be useful to define the following notation. So we are going to define essentially what Uttam Bhai was asking. So we'll define a projector onto the symmetric subspaces for us.
Span also, right? Not just the set.
Yeah.
The span of this set.
No, this is the set of symmetric sets. Oh, yeah, you can write span.
If psi is invariant, then any linear combination will also be invariant.
Yeah, this forms a actually I don't have to say that. I don't know why I said that. No, this is correct because I'm not restricting to any orthonormal base rates. I'm saying all psi's such that they're invariant. So this by itself forms a subspace. You don't have to say that you span it's equivalent.
Okay, I agree. You are not saying the linearly independent.
Yeah, I'm not describing a basis. I'm just saying that any psi which is invariant under all permutations is going to be a part of the set.
Just to confirm, it's not a state, right? Like psi is any normal vector, not a state. It's not.
Yeah. You're right. Otherwise, yeah, normalization might be a concern. Yeah. So this is just a vector. It doesn't have to be normalized. Yeah. At least the way they're defining it. Yeah. Otherwise, it would probably not be a space, right? Because you have to have 0 somewhere. So that would be like a ball or something. Won't really be a space. Yeah. Anyway, that's not so crucial. So okay, so you have 1 by k factorial sum over pi sk vd pi. Okay, so this is just the definition. Okay, so we define this p sim, this object. A priori it's not clear what this does, but it turns out that this will be a projector onto the symmetric subspace. So that's the fun thing, and so let's prove that. We should be able to do it in about 5 minutes. Projection on symmetric subspace C D. Okay, so the theorem states that PDK is the orthogonal projector on the subspace or onto the subspace sim K CT. Okay, so
This is not Hermitian operator, right?
like it's itself adjoint. Yeah, we'll prove it.
It's self-adjoint.
We'll prove it in a minute. So let's start. Okay. So okay, to be a projector, we have to show that p square is p, right? So we'll show p square is p. To be orthogonal, we have to show p dagger is p, right? And we'll show that the image of p is contained in the symmetric subspace, and conversely, the symmetric subspace is contained in the image of p.
Orthogonality, you say something else, right? Not predicate. Orthogonal to what?
Orthogonal, what are orthogonal matrices? I thought A transpose, isn't that A transpose A's identity? No. I mean, I looked up what orthogonal meant, and there was like a more detailed discussion which did not seem applicable here, but I don't know precisely what
You
definition.
have to define, like, because these are operators, right? So you have
Yeah.
to define inner product, and that inner product has to be 0. So trace of p dagger p should be 0. But
Wait, what?
does not
Inner
make sense.
product with what? No, I mean that's
Exactly,
not.
that is the question. So orthogonal to what?
Normally, it's orthogonal to the subspace itself. Yeah, let's not let's look at it later. Let me finish the remaining parts of the proof. So let's forget the orthogonal part. I'll prove that it's a projection, and I'll double check what orthogonal really means. I'm also not fully convinced. It had something to do with the, so if you have some subspace, then the projector has to be orthogonal, like the vectors, but it's not very clear. Okay.
Has to be orthogonal to the remaining subspace of the full subspace. Full space.
Yeah, I think this part sort of establishes that, I think, because you can sort of diagonalize it in terms of the spaces, right? So this would be the symmetric space, this would be the other one, and then because you're exactly characterizing this, yeah, it's orthogonal to the other space. So I think maybe this part actually establishes the orthogonal aspect.
I would like to p into identity minus p is 0.
P into
Identity minus p. So whatever is space on which p is defined.
yeah, that would probably be true in this case. But I thought it's true for, isn't it true for all projectors? P minus p square.
So that already then satisfies orthogonal projector. You don't need to. I mean, yeah. So if you prove p dagger equal to p, then you are right. So you prove p square equal to p and p dagger is also equal to p. Then from like inner Hilbert-Smith inner product, you will have.
Oh, like you're saying that the inner product between these two is Hilbert.
That will be defined p dagger times.
Yeah,
p
sure.
dagger is p, so you get.
I see. Okay, good. Thank you. Yeah. So that does sort it out. Great. Okay. I hadn't thought of it precisely, but yeah, one can formalize it as this if you. I was just thinking of it in terms of this, that like once you know the spaces are different, then it's just, you know, you can diagonalize it and then it's clear that it's in the orthogonal subspace. Oh shoot, we're out of time. No, I'm trying to decide if it's fine. Let's do at least p square is p. Okay, so we at least have some progress. We didn't leave the thing. Okay, so the first note is Vd pi acting on p symmetric. So I'm just going to write p. Okay, so p is so I'll just write this as p shorthand. Symmetric here. So I'll just write. Okay, so Vd pi is the same as Vd pi acting on p is the same as p. Okay, so why is that? So Vd pi acting on p is just the same as 1 by k factorial. Writing the definition here, sum over sigma, right? Vd pi, Vd sigma, right? And this is going to be 1 by k factorial. So this you can write as pi sigma, right? Right, that's not a problem. And then you can update your summation variable, right? So this basically is the same as pi. So I'm skipping like a step or so, but you get it, right? Just updated the summation. Okay, good. So this part is fine, and NB2 is that p square is p. Okay, to see this, what we're going to do is we'll write p square as follows. So we'll write.
Sum over pi, that will be.
Yeah, so sum over pi, Vd pi, right? So I just wrote the first p, okay, multiplied with p, right? But then from this note, we already know Vd pi is, Vd pi on p is the same as p. So, you know, this is just the same as p, right? Because this thing will act on p, give you p. This will, it's independent, and this sum is k factorial, it's normalized. Okay, good. So let's stop here. Next time we'll prove the dagger and the remaining properties. Okay, thank you. Oh, feedback. It is nice when the proofs are small and cute.
Very useful.
And also if you did the last time.